Hi, welcome back to educator.com. Today we're going to talk about piecewise functions. So far, all the functions we've seen use a single rule over their entire domain. No matter what goes into the function, as long as it's part of the domain, the same process happens to that input. So for example, consider x squared plus 3. The same process happens no matter what input goes in. While f of 1, f of 27, f of negative 473, these all produce different outputs, but the function's doing the exact same thing to each. It squares the input, then it adds 3. f of 1 is 1 squared plus 3. f of 27 is 27 squared plus 3. f of negative 473 is negative 473 squared plus 3. Different inputs will make different outputs, but ultimately the process we're going through is the same for each one of these. What if the rule wasn't always the same, though? What if the rule we used, the process we used, changed depending on the input? Instead of always using the same process, the transformation could vary based on what goes into the function. This is the idea behind piecewise functions, functions that do different things over different pieces of their domain. Let's start off by looking at two analogies to get this idea really into our heads. First analogy, imagine you are cooking potatoes, and you're going to turn them either into mashed potatoes or French fries. Now, since the large potatoes make better French fries, you decide to turn your big potatoes into fries and to mash up the small potatoes, right? You just bought a big pile of potatoes, so you've got some big potatoes and some small potatoes. So some of them are going to make better fries, and some of them would probably make better mashed potatoes. So the big ones will become fries, and the small ones will become mashed potatoes. Okay, makes sense. When you start cooking, you begin to work through your pile of potatoes. You pick up one potato at a time, and you start off by deciding if it's small or if it's big. If it's a small potato, you boil it and mash the potato. If it's a big potato, you cut it up and turn it into fries. Seems pretty simple, but we're getting sort of that idea of piecewise functions here, because in both cases, something will happen to the potato. The potato will go through a process, but the transformation is different depending on the type, depending on what kind of potato we have, right? If it's a big potato, if it's a small potato, different processes are going to occur next. We have to pay attention to what we're putting into our cooking process before we know what steps to take next. Another one. Here's another analogy. Let's consider a factory. So imagine this factory where, depending on what materials you bring to the factory, it produces different things. If you bring along 2 kilograms of wood, they make a chair. If you bring in 400 kilograms of metal, they make a car. So 2 kilograms of wood, the factory, it makes a chair. You bring in 400 kilograms of metal, the factory, it makes a car. Now, notice that it's not enough to simply say how much material you bring, right? If you bring in a mass of 400 kilograms, that's not enough information. We need to know, is it wood or is it metal, right? If it's wood, then 400 kilograms of wood at 2 kilograms for a chair means we'll make 200 chairs. But if it's 400 kilograms of metal, well, it was 400 kilograms of metal to make one car, so you'd get one car. So 400 kilograms isn't enough information. We need to know 400 kilograms and what type it is. We need to know what category it belongs to. So something's going to happen to the material no matter what, but we have to know the category that the material belongs to. We have to know what we're putting in, not just a specific number, but what sort of group it's from, before we can tell what's going to happen. So this is now a vague sense of piecewise functions. We've got this idea that a piecewise function is something where a process will happen to the input, but different things will happen depending on the specific nature of the input. That's a really good sense for what a piecewise function is. So now let's consider the notation that's used for piecewise functions. Generally, it's f of x equals bracket, and this bracket just says that it breaks into multiple different things. There's different possible paths that we can take. So transformation rule 1 is our normal rule, like x squared plus 7, and then it says x is in category 1. So what that means is we look at our input, and then we go and we look at the various categories we have, right? Is x wood? Is x metal? Is the potato big? Is the potato small? So we look for which category it belongs to. Once we've found, oh, hey, it belongs to category 2, then we go ahead and we use transformation rule 2 on that input. So we look at the input that's going into the function, we then see which one of the categories it belongs to, and that tells us which of the rules to use. So when we want to talk about the function, we've got this bracket so we can see all the possible rules at once and all the categories that go along with the possible rules. Which set of circumstances do we use each rule under? So given some input, we first check which category it belongs to, then we use the corresponding transformation. So there are all these transformation rules. We first check the category, then we use it. Also, notice that since f is a function, because f is a function, two categories cannot overlap. So categories cannot overlap. Why? Because if they overlapped and they had different rules, we'd get two different outputs from using the same input. We'd get two different outputs from using two different rules if the categories overlapped. Remember, a function, if we put in x into a function, it has to only produce one output. If we put in x into a function, it can't spit out a and spit out b. It's not allowed to produce two different things. So if we put in x and x belongs to two different categories, each of those rules would have to either be the same thing or that we have to make sure the categories don't overlap. So we are allowed to have categories overlap, but if that's the case, we have to make sure that the transformation rules produce the same output during that overlapping space. Otherwise, we've broken the nature of being a function. All right, let's start looking at some examples to help us get a sense of how to use this notation. So this isn't really formal mathematics, but we can get an idea of how this notation works by seeing how it would work on those previous analogies. So first off, our potatoes analogy. Potatoes of input. So how does our potato function work on input? If we plug in x, the first thing we do is we see, oh, okay, is x small? If x is small, then we turn it into mashed potatoes. If x is big, then we turn it into French fries. So we plug in our potato x, and then we see which category does x belong to. Same sort of things going on at the factory. If we plug in x, our input into the factory function, some sort of, quantity, some number of kilograms of a material. We then say, okay, is x wood? If x is wood, it is x over 2, because remember it took 2 kilograms of wood to make one chair, so it's x over 2 chairs. Or if x happens to be metal, it's x over 400 cars, because it was 400 kilograms of metal to make one car. So we plug in the x, we take the x, we see which category it belongs to, then we plug it into the appropriate rule based on the category. Great. All right, so let's see an example of the piecewise function actually working through with numbers. So here is a table. This is the most extreme sort of table we can use. When we're actually practicing this, doing this, we probably won't want to use a table that has this much possible information in it, but we'll get the idea of how piecewise functions work from this table. So to start off with, let's look at what would happen to -4. Well, actually, first let's look which one would -4 belong to. -4 would be in x is less than -1, right? So it's going to belong in x squared minus 1, and it's not going to belong in the 2 rule, because -4 is not between -1 and 1, and -4 is not greater than 1. So it's going to knock out these 2 rules. Next up, -3. Well, -3 is still less than -1. So once again, that knocks out the second rule and the third rule. What about -2? Well, once again, -2 is still less than -1. So that knocks out the second rule and the third rule again. What about if we plug in -1? Well, -1 is not less than -1, right? -1 equals 1. So hey, we've got this less than or equal right here. So -1 less than or equal knocks out that first rule, but -1 is still not greater than 1 from our third category, so it knocks out the third rule as well. What about plugging in 0? Well, 0 is not less than -1, and 0 is not greater than 1, so our first and third categories just got knocked out, first and third rules out. What if we plug in 1? Well, once again, 1 is equal to 1, so it's part of this second category. So 1 is not less than -1, so it knocks out the first rule, and 1 is not greater than 1, so it knocks out the third rule. We get to 2, and finally 1 is less than 2. 2 is greater than 1. We've got 1 being less than 2, so we're using the third rule, which means that our first rule and our second rule are knocked out. What about 3? 3 is still greater than 1. 3 is not less than -1. And 3 is not between -1 and 1, so those rules and categories are out. What about 4? 4 is not less than -1. And 4 is not between -1 and 1, but 4 is greater than 1, so only the third rule gets used there. So now we've got a sense of how this table comes together. So now let's actually start plugging in numbers. So -4 goes into x squared minus 1. Well, -4 squared minus 1 gets us positive 16 minus 1, so we get 15. What about -3? We plug in -3 squared minus 1. That gets 9 minus 1, so we get 8. What about -2? We plug in -2 squared minus 1. So 4 minus 1 gets us 3. All right, now we switch rules. For this one, we plug in -1, but -1, it doesn't really do anything. All the function says is if you're between -1 and 1 as your input, it outputs 2. It doesn't care what you're putting in as an input as long as it's between -1 and 1. It's going to be constant. It's going to always give the same thing in there. So it's going to just be 2, 2, 2. 2 for all of those. -1, 0, and 1, it's 2. It's going to be a constant value of 2 in that interval. Now we switch rules once again, and we're at 2. -2 times 2 plus 4. -2 times 2 gets us -4. -4 plus 4 gets us 0. What about 3? -2, plug in our 3 plus 4. -2 times 3 gets us -6. -6 plus 4 gets us -2. Plug in 4, -2 times 4 plus 4. -2 times 4 gets us -8. -8 plus 4 gets us -4. We've managed to fill out this table. So the important thing is to start off by figuring out which one of these inputs is going to go to which category. Where are my inputs going to go? You have to figure out an input and its connection to which of the possible categories it can be connected to. All right. Let's also see an example of a non-numerical piecewise. So many lessons ago, when we first introduced the idea of a function, we talked about a non-numerical initial function. It took a name spelled with the Roman alphabet and output the first letter of the name. Like, for example, if we gave it the name Robert, the initial function would come along and it would say, hey, your first letter is R, so we put out the letter R. Done. So it's just going and saying, hey, let's grab the first initial and do that. That was our idea of the initial function when we first introduced it. We can have functions operating on non-numerical things. Well, we can also have piecewise functions on non-numerical things. We can modify that and make a piecewise function. So we'll have f of x is equal to 2 categories. So 2 categories. Our first rule will be the first letter of x, the first letter of the name, if the name starts with a to m. So x is just a placeholder for a name here. The first letter of the name if x starts with a to m. And then the last letter of the name if the name starts with n to z. And notice that that covers all the possible letters a name could start with: a to m, n to z, a, b, c, d, e, f, g, h, i, j, k, l, m, n, o, p, q, r, s, t, u, v, w, x, y, z. Great. So Albert, we plug in Albert, and Albert belongs to the red category. It belongs to starting with A to M. That one's pretty easy, so we use the first letter. So it gets A as the letter out of it. What about Isabella? Well, Isabella is between A and M, right? A, B, C, D, E, F, G, H, I, J, K, L, M, M. So Isabella also belongs to the red category, so it's going to return in I. What about Nicole? Nicole is in N, right? So it's using the blue category, so it uses the last letter of the name. So the last letter of Nicole is E, Nicole. Vincent begins with a V, which is between N and Z, right? M-N, N-O-P-Q-R-S-T-U-V, W-X-Y-Z. So we're going to be using the blue category, the second category. We're going to use that last letter, T. What about Zach? If we've got Zach, Zach's pretty clearly going to be starting with a Z, so that means we're in the second category. We're going to cut off that last letter. We're going to get the last letter, and it will be H. So we can have a piecewise function operating on non-numerical things. The idea of a piecewise function is just we take in things, we see which category the thing belongs to, and then we apply a rule based on the category it belongs to. We figure out the category, then we apply a rule based on it. Great. Graphing piecewise functions. So how do we graph these things? It's actually really similar to graphing a normal function. A series of points x, comma, f of x, right? When we graph x squared, the reason why 0, 0 is a point is because if we plug in 0, we get 0, right? 0, comma, f of 0. for x squared would get us 0, 0. Then we plug in 1, f of 1, because we plug in 1 and it gets 1 squared, so 1, 1. We plug in 2 and we get f of 2, so that would be 2, then 2 squared, 4, so we'd be at 2, 4. We're moving to a height of 4, and that's how it's working for x squared. And that's how it works for graphing any function. We put in the input, and then we see what output does that get to. The difference with a piecewise function is that the rule determining where x is going to map will change depending on which x we're looking at. So often it will look to us like the graph is changing at switchovers, that we are breaking from one thing to another, and in a way we are. We're switching between rules. So when x switches from one category to another, the shape or location of the curve can change because all of a sudden we're doing a new way of outputting things. It's not that nice smooth connection anymore because we're working all through x squared. All of a sudden we're jumping from x squared to maybe x cubed minus 1, and we're going to see suddenly a new, totally different kind of output when we change categories. An important graphical note is that to show inclusion, we use a solid circle. So solid circles say this point is here. This point is actually being included. We show exclusion, excluding it, saying it's not there, with an empty circle. So empty circles give us exclusion. So exclusion is an empty circle. Inclusion is a filled-in circle. That way, when we have two categories like x is less than 1 and 1 is less than or equal to x, we want to be able to know which curve owns x equals 1. And because it's less than or equal to, we'd have 1 is less than or equal to x. So it would get the dot at that point, and x less than 1 gets to go right up to 1, but it doesn't actually get to include 1, so it uses the exclusion, the hollow, empty circle. Let's see an example. If we graph f of x equals quantity, not quantity, but x squared minus 1 when x is less than negative 1, 2 when negative 1 is less than or equal to x, which is less than or equal to 1, and negative 2x plus 4, which is when 1 is less than x, we would see this graph right here. And I also just want to point out, that's what we just did, our table, our really big table where we figured out all the possibilities. That's what we just did a few slides back. So x squared minus 1, we see this portion, I'll make it in blue actually. We see this portion of the graph right here, because x squared minus 1, it's a parabola, so we're seeing the left portion of the parabola because it's only the portion of the parabola when x is less than negative 1. We plug in those values and we see where it gets mapped. However, because it's x is less than negative 1, we've got exclusion right here. We're not allowed to actually use that point. It gets right up to it, but it can't actually touch x equals negative 1 because it has exclusion on x is less than negative 1. It's strictly less than, it's not actually allowed to equal negative 1. Similarly, we've got to flip to inclusion on the rule of being 2, so it gets to include it on this, and then it's just a constant from negative 1 up until 1, so we've got this nice straight line here. And then in green, negative 2x plus 4, 1 is less than x, we've got this thing right here. Now, why don't we see a dot at this junction right here? Well, because it's actually agreed on. This point shows up here, and it would show up here if it were able to hold it. Negative 2x plus 4, evaluated at 2, if we were to have that, not 2, but 1, because we're at the point 1. 1 is our changeover right here. 1 is less than x, and x is less than or equal to 1. So negative 2, plug in 1. Negative 2, plug in 1 plus 4. We get negative 2 plus 4, so we get 2 if negative 2x plus 4 was allowed to use x equals 1, it would wind up agreeing with it. So it's actually going to the exact same point. So it's sort of a hollow for negative 2x plus 4, but then it immediately gets filled in for 2. So ultimately, we don't see a break there. There's no loss, because while one end is excluding it, the other one is including it, and they're on the same place. So we wind up only seeing the inclusion. It's held there. They're together in that place. And that's one example of graphing a piecewise function. All right, this is a great time to bring up the idea of a continuous function. We're going to occasionally refer to the idea in this course, and it's going to come up a whole bunch in calculus, so it's important to get used to it now. It's hard to formally define continuous right now. Right now, we don't have enough sort of symbolic technology. We aren't used to using symbols in the way we need to talk about continuous. We can't really talk about it with numbers right now, but we can understand what it means graphically. It makes great intuitive sense in pictures. All of these different things, all these three different ways of talking about it, all mean the exact same thing. So if a function is continuous, all the parts of its graph are connected. Its graph could be drawn without ever having to lift your pencil off the paper, and there are no breaks in the graph. These three things all mean the exact same thing, right? The parts of the graph are connected, means that there's no breaks, and if there's no breaks, then you could just put your pencil down and draw the whole thing without ever having to lift your pencil off the paper. Three different ways of thinking about it, but they all mean the same thing. The whole thing is connected. It is a continuous flow. It's this nice connected piece of information. Great, let's look at some examples to help us understand this. For a function to be continuous, it must be any one of the below statements. We just said them, let's say them again. The parts of its graph are connected, the graph could be drawn without ever lifting your pencil or pen off the paper, and there are no breaks in the graph. So here's one example of something being continuous. So even though it's got this sort of like juke, right, it suddenly changes direction there in this corner, it's still continuous because the graph connects in this corner. The two ends touch. You can draw it in one smooth thing without ever having to take your hand off of drawing. You could draw it in one smooth thing without ever having to lift up. So it is a continuous graph, at least in that viewing window, what we can see. Now, here's an example of something being not continuous. This one right here is not continuous because we've got this break. All of a sudden we jump locations, right? We have an empty circle here and we're now all of a sudden in a totally different place. If we were to try to draw this, we could get up to here, but to go any farther we'd have to lift our pencil up, move down, and now start down here, so we'd be in a totally different place. There's a break in the graph. The parts of the graph are not connected. It's not just one nice connected curve. It's not a continuous function. Finally, another one that's not continuous. This one is pretty close to being continuous, right? We can draw and draw and draw and draw and draw, but there's an empty point here. We've got one point. We've got this single discontinuity. This single point has been moved off of the line. We have to move down here to draw on this single point, and then we go back to normal. So it's really, really, really close to being continuous, but it's not perfectly continuous because of this point here has been sort of moved down here. It's in a different place. It's not where it needs to be continuous. So continuous function, all the parts of its graph are connected, and that means even one point could be out and it would break the continuity, it would break being continuous, it would no longer be connected. Great. Interesting functions. So at this point, it's probably becoming clear that you can have some kind of weird looking functions, right? So far, over the course of algebra and geometry, you've seen pretty reasonable looking things like x squared, square root of x, x cubed. Even the weirdest things you've seen have been pretty reasonable, just sort of smooth curves. But we're starting to see with piecewise functions, things can be a little odd. So let's look at another one, a rule that's a little more complex than x squared, something that's a little more interesting than the ones we've been used to so far. So here's an example, the step function. Sometimes it's also called the greatest integer function, and it will make sense why in just a second. So f of x equals double bracket x on both ends, so it's just, make a bracket, make another bracket, put x inside, and then close both of those brackets. The greatest integer less than or equal to x. What does that mean? So greatest integer less than or equal to x, let's try it out. So what would happen if we put in 3? Well, the greatest integer that's less than or equal to 3 is 3, right? Because 3 is an integer, and there are other integers out there like 2, but 2 is not the greatest possible integer that's less than or equal to x, right? Since there's -1, 0, 1, 2, 3. 3 is the greatest one that is less than or equal to 3. What if we went higher, if we said 4? Well, like 4 would be greater than 3, so it's not in the running, it doesn't have a possibility, so that would be 3. But what if we tried something that wasn't just already a straight integer, like say 4.7? If we plugged in 4.7, well, what is the greatest integer that is less than or equal to x? Well, 3 is a possibility, 4 is a possibility, 5 is a possibility, and it would keep going in either direction, right? Well, so if we went from the left, let's start like this. So we could say, hey, 1. 1 is a possible thing. Let's go with 1. Oh, well, if we look at 2, well, it turns out 2 is even bigger than 1, and it's still less than 4.7, so 2 is our best option. Oh, what about 3? Well, 3 is still less than or equal to 4.7, and it's bigger than 2, so it's the best option. Oh, what about 4? Oh, hey, 4 is bigger than 3, and 4 is less than or equal to 4.7, so it's the best option so far. What about 5? Oh wait, 5 is greater than 4.7, 5 is greater than 4.7, so it's not in the running because it has to be the greatest integer less than or equal to x. So that means 5 is out of the running and also anything larger than 5. So everything less than 1, 2, 3, those aren't going to work because we found 4 in its best so far, and everything 5 or greater isn't going to work, so that means our answer is 4.7. It's basically always rounding down. 4.7 would become 4, 3.5 would become 3, negative 2.5 would become negative 3 because we have to round down, and what's below negative 2.5? Negative 3. All right, and finally, we can also sometimes call this the int x, the integer function on x. Sometimes you'll see it denoted as that. It'll be written as int x as opposed to double bracket of x. You know, same idea though, this greatest integer thing, this step function we were breaking. Now, why is it called a step function? We'll look at a picture and that'll help explain it a lot. So the graph of f of x equals step function looks like this. Why does it look like this? Well, remember, at negative 3, where do we get placed? Well, negative 3 is an integer, so it just goes right here. Well, what about anything in the middle? Anything in the middle would get placed onto negative 3 because they'd have to be rounded down to the greatest integer they're connected to. So that's why we get there. As soon as we get to negative 2, though, we're going to jump up because negative 2 is an integer, so it gets to be used here. And so it's going to have the same sort of thing. Anything in the middle would wind up getting placed onto negative 2. But once we get to negative 1, we make it to this one, and so on and so forth. And so we just keep stepping along and stepping along and stepping along. And every time we hit an integer, we jump up to the next height, and so on and so forth. And so we got greatest integer less than or equal to x winds up looking like a staircase in terms of its steps because we keep stepping up every time we hit a new integer. Cool. All right, ready for some examples. So first one, just to get started, let's evaluate this function at 4 different points. F of x equals 3x plus 10 when x is less than negative 1, 8 when x is equal to negative 1, and x squared minus 10 when x is greater than negative 1. All right, so at f of negative 3, first what we got to do is we got to say, oh, which category do you belong to? Well, negative 3 is less than negative 1, so it belongs to the 3x plus 10 rule. So we use 3x plus 10. We plug in the negative 3. We've got 3 times negative 3 plus 10, negative 9 plus 10. So we've got 1. F of negative 3 equals 1. Great. What about f of negative 1? F of negative 1, what does that belong to? Well, negative 1 equals negative 1, so it's using this category right here. So that means we've got 8. So we've got 8. There's nothing else that we have to do. It's already as simple as it can be. F of negative 1 equals 8, and that's our answer right there. What about f of negative 0.9? So this one, well, it's really close to negative 1, but remember, this thing was x equals negative 1. It only happens on precisely negative 1. So negative 0.9 is, in fact, slightly greater than negative 1. So negative 0.9 is greater than 1, so we use the rule x squared minus 10. We plug in that negative 0.9. We've got negative 0.9 squared minus 10. Negative 0.9 squared is 0.81 becomes positive. Anything squared becomes positive as long as it's a real number. 0.81 minus 10. 0.81 minus 10 becomes negative because the 10 is bigger, negative 9.19. So f of negative 0.9 is equal to negative 9.9. Finally, one more example, f of 5. F of 5, which category does this belong to? Pretty clearly belongs to x is greater than negative 1. So 5 is greater than negative 1, so we use the x squared minus 10 rule. Once again, use that process. Plug in the 5. 5 squared minus 10. 25 minus 10 is 15. So f of 5 equals 15. And there we are. And that's how you evaluate a piecewise function. You see which category it belongs to, then you plug it into the appropriate rule, and you just plug and chug like you're doing a normal function at that point. Great. Next one. All right. This one will graph a piecewise function. So our function this time is f of x equals x plus 6 when x is less than or equal to negative 3, and negative x squared minus 2x plus 1 when x is greater than negative 3. So first off, let's make a table to help us graph this thing. So x and f of x. So what would be a good place to start at? Well, we've got negative 3 showing up here and here, so that's probably going to sort of be the midpoint, mid sort of zone in our graph. So let's start by plugging in negative 3, and we'll go, more negative as we go up, negative 4, -5, -6, and we'll go more positive as we go down, -2, -1, 0, 1. Great, so let's try plugging in, which rule will we wind up using? Well, when x is less than or equal to -3, we will wind up using the things that are above -3 or equal to -3. So this rule up here gets the x plus 6 portion, and down here, when we're below the line, we get -x squared minus 2x plus 1, because then x is greater than -3, right? -2 is greater than -3, 0 is greater than -3, etc. All right, so let's try doing some of these. So if we plug in -3, -3 plus 6, that's going to equal +3. -4 plus 6, -5 plus 6, -6 plus 6. What do these all come out to be? -4 plus 6 gets us 2, -5 plus 6 gets us 1, -6 plus 6 gets us 0. So we've got a pretty good idea of how to graph the x plus 6 portion, the portion of the graph where x is less than or equal to -3. Now, what about going the other way? Well, if we plug in -2 into -x squared minus 2x plus 1, we've got -2 squared minus 2 times -2 plus 1. Let's plug in all of them, then we'll just do them at once. -1 squared minus 2 times -1 plus 1. -0 squared minus 2 times 0 plus 1. -1 squared minus 2 times 1 plus 1. What do these all come out to be? Well, first off, -2 squared becomes +4, so we hit that with another negative, and we've got -4 right here. -2 times -2 gets us +4 plus 1, so -4 plus 4 gets us canceled, and then plus 1, we get 1. -1 squared gets us +1, but then hit with another negative, we get -1. -2 times -1 gets us +2 plus 1. So -1 plus 2 plus 1, we get 2. 0 squared gets us 0. -2 times 0 gets us 0. Plus 1, we get 1. -1 squared gets us -1. -2 times 1 gets us -2 plus 1. So we get -2 here. Great. All right. So at this point, we can start graphing this thing. So we're graphing from -6 to 1. And our extreme y values are, we've got from 0, 1, 2, 3. So we'll make, 1, 2, 3, 4, -1, -2, -3, -4, -5. That's probably enough information to have to do down there. 1, 2, 3, 4, -1, -2, -3, -4, -5. And there doesn't seem to be any reason why we shouldn't do this on a square axis. So the tick mark length, the length of our vertical tick marks, can be the same as our horizontal tick marks. And of course, I'm just doing this by hand, so it's approximate, but this isn't too bad. 1, 2, 3, 4, 5, 6, and it would keep going out that way as well. All right, so -1, -2, -3, -4, -5, and -6, +1, +2. Great, so at this point, we plot down our points just like we're doing a normal thing. -6 goes to 0, so -6 goes to 0 right here. -5 goes to +1 here. -4 goes to +2 here. -3 goes to +3 here. And at this point, we've got the line portion. Does the line keep going to the right, though? No, because it stops once x goes greater than -3. It only works on the rule only happens when x is less than or equal to -3, but it would keep going off to the left. So it stops right here, but it does include that point because of the less than or equal. Now, what about the parabola part of it? Well, we plug in -2. -2 gets us 1. -1 gets us 2. 0 gets us 1. 1 gets us -2, and 2 would continue down. So we've got a pretty clear parabolic arc going on here. We're used to this, and it's going to keep going off, straight off forever to the right because it's x greater than -3. So as long as we're continuing to go to the right, it will continue on. What happens to the left, though? So we know what's happening. It's going to be in a parabolic arc, but we're not quite sure where it's going to land because it's got to stop somewhere. but we don't know what height it will stop at. We know it will stop at just before -3, right? So it'll stop at -2.9999999999999, right, forever, continuing forever and ever. It can't actually touch -3, but it can get infinitely close and get right up next to it. So let's figure out where would it be going if it got right up next to it. So what we do is let's see what would happen if we plugged in -2.99999. Now, and I mean even more nines, right? -2.999999999 forever. Now, well, not quite forever because then it turned into 3, but the point is -2 point lots of 9s. Now, I don't know about you, but I don't want to have to plug in -2.9999999 into a calculator because it's going to get me these ugly numbers and I'll wind up having decimals. And really, when you get right down to it, isn't -2.9999999 going to behave an awful lot like if we'd plugged in -3? It's so close to -3, we could probably just plug it in as if we'd plugged in -3, and indeed we can do that. We'll just know that it will be an empty circle at that because it's got exclusion, it's got strictly greater than. So we'll plug in -2.999999999, which still belongs to the -x² minus 2x plus 1, because -2.9999999 is greater than -3, if only by a little tiny bit, and it's going to behave pretty much the same as if we had plugged in -3, so we can calculate it more easily by plugging in -3. So -3 squared minus 2 times -3 plus 1. What's that come out to be? -3 squared becomes -9. -2 times -3 becomes +6 plus 1. So we've got -9 plus 7 equals -2. So we know that this is going to go out to -2 when it gets to -3. But it's not actually going to be at -3. It's going to be hollow there because we're excluding it. It's not actually allowed to go to that point because the exclusion was already put on that first category, on that first rule. So this will curve down in a parabolic arc into the exclusion hole and then just stop right there. It doesn't actually get to touch -3, but we can basically calculate it as if it had gotten to -3 because -2.99999999999 is so close to being just like -3. We can calculate it as if it had gotten there, but then we just have to remember we have to make sure we put it in this circle here because we're actually excluding it at -3 because x isn't equal to -3 if x is greater than -3. Great. All those ideas that we just talked about, they're going to come up a lot with this. Let's go just a little bit off and pretend that we're using the real number and then see what it's like. And we're going to do that here. So if what I do here doesn't quite make sense, look back at the explanation of that 2.9999999 thing, and we'll get an idea of, oh, that's why we can do this sort of thing. So once again, we'll set this up in the same way. X, f of x. Now, what values? Clearly, -2 is kind of important. It shows up in a lot of places. What are we going to do? Well, the first thing that we are told to do in this problem is we're told to figure out, give the domain of f, then graph it. So first, let's do the domain. So domain, how do we come up with the domain? Well, remember, domain is all of the inputs that are allowed to go into a function. x² minus 5, hey, x² minus 5, it never breaks down. 3 never breaks down. -2x plus 1, it never breaks down. So none of the rules break down. So none of the processes, none of the rules, break. They're always defined. However, are the categories always defined, right? X is less than -2 means we can just keep on going. We can keep on going. So it's really -infinity less than x. So we can go all the way down to -infinity. What about to the right, though? Is there anything that we're not allowed to get to? Well, -infinity up to -2, and then -2 is here at equal, and then -2 is less than. So we've covered all of our bases from -infinity up to -2 and keep going up until 1. Is there any rules for what happens if x is greater than 1? No, we don't have any rules. We've got x is less than -2, x equals -2, and -2 is less than x, which is less than or equal to 1, but we don't have any rules for when x is greater than 1. So no rules for x greater than 1 means that f doesn't tell us what to do if we're plugging something in, right? The f fails to tell us what to do to this input if we plug in something that's greater than 1. If we plug in, say, 500, we look at this and we say, oh, this doesn't belong to any categories, so f is undefined at 500. It doesn't work. It's not in the domain. So the domain fails to contain everything in x greater than 1. So that means our domain is not going to be x greater than 1. That's the things of failure because we don't have rules. The domain is everything from negative infinity. We use parentheses for negative infinity, any infinity. And we go up until 1, and we include the 1 because we've got less than or equal to, but we can't go past it. We've got no more rules to go up past it. So f has a domain from negative infinity up until 1, including 1. Great. Now let's build out that table. So negative 2 seems like a good place to sort of make our middle. And if we are above negative 2, we will use which rule? We'll use the x squared minus 5 rule. If we are, sorry, by above I meant to say more negative than negative 2. And if we are below on this table, which is to say more positive, closer to 0, we are going to use negative 2x plus 1. So negative 2 will have negative 3 and negative 4, negative 1, 0, 1. But just like we did in the last thing, it'll be useful to know where is it going if it had been allowed to get to negative 2. So for the above part, we'll say negative 2.0001 and negative 1.99999, right? These things, because negative 1.99999 is greater than negative 2, and negative 2.000001 is less than negative 2, but they're going to behave effectively as if we had plugged in negative 2. So when we're actually figuring out the numbers, we can pretend as if we had plugged in negative 2, just to make it easier on us to do the calculation. All right, first one off, negative 2. What are our f of x's? Negative 2, well, negative 2's rule just says spit out 3. Doesn't matter what your input is, even though we have to use the category of negative 2. So it automatically spits out 3. So 3 at negative 2. What about negative 2.0001, which would use the x squared minus 5 rule? Well, that's about the same thing as plugging in negative 2. So we've got negative 2 squared minus 5. Well, keep going. Let's just keep going up to get them all written out. Negative 3 squared minus 5 and negative 4 squared minus 5. What do those all equal? Well, negative 2 squared becomes 4, 4 minus 5, so negative 1. Negative 3 squared, 9, 9 minus 5, negative, oh, sorry, not negative 4, but positive 4. 9 is bigger than negative 5. And negative 4 squared, positive 16, 16 minus 5, 11. Okay, what about the other way? If we go towards the negative 2x plus 1 rule, well, if we'd plugged in negative 2, we'd get negative 2 times negative 2. We aren't literally plugging it in, we're just saying, what if we had gone all the way up to it? Let's see what would have happened, even though ultimately we'll have to exclude it because we've got this strictly less than, strictly greater, these strictly less than signs, strictly greater than signs. So negative 2 plus 1. Negative 2 times negative 1 plus 1, negative 2 times 0 plus 1, 1 times 0 plus, oh, sorry, not 1, whoops, sorry about that. Negative 2 times positive 1, got that confused with the 1 above it. Negative 2 times 1 plus 1, what do those all equal? The thing that is effectively going to be like negative 2 times negative 2, positive 4, 4 plus 1, 5, negative 2 times negative 1, positive 2 plus 1, 3, negative 2 times 0, 0 plus 1, 1, negative 2 times 1, negative 2 plus 1, negative 1. Great, so now we're in a position to be able to graph it. Our extremes, vertically we can get up to really high things when we're in the x squared minus 5, so we won't worry about the 11 part. But we're sort of going between like around like extremes of like 5, maybe a little lower. So let's graph, we'll graph this. We never get to very low values, it seems, so we'll put our corner down here. And we also never get past 1. Remember, our domain is only negative infinity up until 1, so we also don't have to have a whole lot of stuff on the right. So we've got positive 1 here, positive 2 here, positive 1, positive 2, positive 3, positive 4, positive 5, positive 6, negative 1, negative 2, negative 1, negative 2, negative 3, negative 4, negative 5. Great, and that's plenty of room because we only wound it up to negative 4, and we know that x squared minus 5 is going to blow out. So 1, 2, 3, 4, 5, 6, negative 1, negative 2, 1, 2, 3, negative 1, negative 2, negative 3, negative 4, negative 5. Oy, making tables, right? I mean, making axes, right? So let's plug in some things and see what happens. We plug in negative 4, and it goes out to 11, so we can't even see it. It's so high up. Negative 3 gets to 4, though. We can definitely plot that. So negative 3 up until goes to 4, negative 3 comma 4. Negative 2 negative 2 if it had a negative 2. It doesn't actually have it, but we know that negative 2.0001 would practically be going to negative 1. So we're a exclusion hole down here just below the negative 2. At negative 2, though, we actually wind up being at 3. So we have this single point right there. If we had negative 2 for the negative 2x plus 1 process, we'd be at 5, but we can't actually go there. So once again, we have an exclusionary hole there. Negative 1 would be at 3, is at 3. 0 is at 1. 1 is at negative 1. And it stops right there because we stop at 1. We can't go any higher than positive 1. Our domain caps out there. So our straight line, just a straight line up until where it stops at that exclusionary hole. We've got this point in the middle, the 3 point, but it's just x equals negative 2. And then we've got a parabola curving up. It's already moving pretty fast by this point, so it's not going to be a nice smooth parabola like this. It's already moving fast up because it's pretty far up, right? It manages to jump from negative 1 to 4 and then from 4 to 11. So it's not the bottom part of the parabola. It's already in process in a way. So curve this parabola up, and it just zooms way, way off really quickly. All right, so that's basically what we're seeing here for our graph. We've got a parabola on the left-hand side, which drops to the single point. There's just the single point in the middle, and then we switch to negative 2x plus 1, which goes to 1 and then stops at 1 because the category just stops at 1. So it stops right here, and we don't have anything farther to the right. There's nothing further off to the right because the categories don't include anything further to the right. All right, final example. Certain phone company charges $20 for using its service along with 10 cents for each minute under 200 minutes. After 200 minutes, they charge 5 cents per each additional minute. Let's give a piecewise function, p of t, price in terms of t, that will describe the price in terms of t, the minutes spoken. So t is the minutes spoken. So it's pretty easy for us to figure out what the first part is. So the first portion, when we're under 200 minutes, which is to say when t is less than or equal to 200, price of t is not too hard for that. P of t equals, well, $20 flat rate, right? They charge us $20, and then they charge us 10 cents per each additional minute. So $20 plus that additional 10 cents, how many minutes did we have? We had t, so 0.1 times t, right? And that's what it is. Let's do a real quick test. Let's say if we'd talked 100 minutes, then 100 minutes times 10 cents would be $10. So we'd have a $30 total, which if we plug that into our new function that we just made, p of t, p of 100 would be 20 plus 0.1 times 100, which would come out to be 30. Great. So the first part of it checks out. What about the second portion, though? That's where things start to get a little complicated. So in the second portion, when we're over 200, which is to say t is greater than 200, and actually it could be greater than or equal because we know that they're going to have to agree. There's not going to be a sudden jump there. And we'll talk about that more later. It's a way of checking this function, actually. We know that it's going to be 5 cents for each additional minute. So our first thought might be, great, easy. It's going to be 0.05 t. Not true. This is not going to be the case. Why not? Because it's for each additional minute. So it's for each additional minute over 200. So after 200, you get charged at 5 cents per minute. Before that, you still get charged at the 10 cents. So how many minutes over 200? Well, that's not too hard. We know that we have t minutes total. We know that we're already over 200, so it's going to be the number of minutes we've talked minus 200. So t minus 200 is the number of minutes we talked. So it's 0.05 cents times t minus 200. Now, that's the amount of additional money that will be on top of some lump. So how much is it to even make it to 200 minutes in the first place? Well, 200 minutes in the first place, let's see what it is from our first one. P of 200 would be equal to 20 plus 0.1 times 200. 20 plus 0.1 times 200, just move the decimal place over 1, so it becomes 20. So 20 plus 20, 40. So it costs $40 to get up to 200 minutes. So it costs $40 at 200, and then it is plus the additional amount per minute. So for the second portion, our function is going to be p of t equals $40, the lump sum that we have to pay at first to have even made it to the 200-minute mark, plus 5 cents for the number of minutes over 200 minutes. So our function has been broken into two pieces. So we've got a piecewise function here, p of t equals 20 plus 0.1 t when t is less than or equal to 200, and 40 plus 0.05 times the minutes over 200 when t is greater than or equal to 200. Now we know that the two have to agree, otherwise people would make sure to make that jump or not make that jump, because otherwise there'd be no reason to, there's the sudden change of a switch. It wouldn't make sense for the phone company to have it suddenly leap more on your bill or cut off portion of your bill if you were to hit the 200 mark. It's going to just continue in a continuous function, we would expect. So we can check this, and we can check and make sure that indeed p of 200 is equal to 20 plus 0.1 times 200. We already did this before. It was $40. And let's check and make sure that the second portion, p of 200, would it agree 40 plus 0.05 at the minutes over 200, so that's 200. 200 minus 200. Hey, that's just 0, so that cancels out the 0.05, so we get 40. So those two things check. And our function price in respect to time makes perfect sense. So p of t equals 20 plus 10 cents per minute when minutes are less than or equal to 200, or 40 plus 5 cents per minutes over 200 when the number of minutes is greater than or equal to 200. Great. Hope piecewise functions are making a lot more sense now. Remember, it's an idea about put into the category, then apply the rule based on the category. That's the major idea in piecewise functions. If you can hang on to that, you'll be able to make sense of them. All right, we'll see you at educator.com later. Bye.